All right, young scientists, this is a new technology for me, but we're going to try it out, and I apologize for any kinks that there might be, but today we're going to talk about thermodynamics and specifically entropy. Now, first we need to talk about spontaneity. This means when something is spontaneous, that means that it will occur on its own. It'll happen without anything interfering. Being spontaneous doesn't mean something happens quickly or happens slowly. The rate is something completely different that we talked about in Unit 5. Spontaneity just means, is something going to happen on its own? So an example of a spontaneous reaction is steel rusting when it's exposed to oxygen. Now that might happen quickly if it's in some warm water, or it might happen very, very slowly if it's just sitting out in the air. But either way, it's a spontaneous reaction. Thermodynamics and kinetics do not explain spontaneity. Thermodynamics talks about the reactants and the products. Kinetics talks about how the reactants become the products. But we're missing a factor when we want to talk about spontaneity. That factor is entropy, which we designate with the letter S. Entropy is a measure of the disorder of a system, or how chaotic a system is. The first law of thermodynamics you already know. The energy of the universe is constant. This means energy cannot be created nor can it be destroyed. It can just be moved from place to place, and its form can be changed. The second law of thermodynamics is that the entropy of the universe is increasing, or the universe is getting more disorganized, disordered. So when we look at the change in entropy of the universe as the change in entropy of the system, the things we care about, and the change in entropy of the surroundings, everything else in the universe, the sum of these two things should always be a positive number. The entropy of the entire universe is increasing. This doesn't mean that it's always increasing in the system, or that it's always increasing in the surroundings, but the sum of those two needs to be a positive amount. Let's look at some examples. Here I have an ideal gas in a glass container with a stopper holding it off. Now, if I remove that stopper, or if I open it up as we see here, gas particles will be able to flow into the empty side. Now, right now, having them all on one side is much more organized than what we see in the second diagram. So they're more likely to flow across, and right now none of them can flow from the vacuum side to the ideal gas side because there's nothing there to move. So particles will start to flow across and fill this vacuum side until the distribution of the particles is even. Now particles can still go through the tube from one side to the other, but the rate that they go from the second side back to the first and the first side over to the second will be equal. Now we're at equilibrium. A way to think about this is to think about all of the different possible arrangements of the particles. We call these microstates. At the beginning, all of our particles were on one side. There's only one way to make that happen. Then as we start to progress, you can move one of the particles across, but have the rest of them still gathered. Now we have more possible arrangements, so we have more entropy. But in the third example, we have even more possible arrangements with this even distribution. This is the most disordered. It has the most entropy. And so that's what's going to be favored. That's what's more likely. It's not to say that one of these from before can't happen again, but as soon as one of those particles flows across, another particle will flow back and we'll end up with something looking more like scenario 3. Another place we see this is with phases. Solids have less entropy than liquids, which have less entropy, much, much less entropy than gases. Solids really only have approximately one set of positions. All of the particles are set in their crystal lattice and they're stuck where they're at. They vibrate, but they can't really move. Liquids can start to flow freely, which gives them lots and lots of arrangements, but not nearly as many as gas particles, which can flow all around their container and gives them many, many, many more different arrangements. This means that gas particles have much more entropy than liquids, which have more entropy than solids. Now, with this in mind, I'd like you to, in just a second, pause the video as you read through these and decide which answer you think is correct. So I want to know which has the greater positional entropy, solid carbon dioxide or gaseous carbon dioxide. And I also want to know which has the greater positional entropy, nitrogen at 1 atmosphere or nitrogen at 0.01 atmospheres. Now this is in a flexible container, so the volume can change. Go ahead and pause the video and think about it for a minute. Okay, once you've had enough time to think here, first let's compare the solid carbon dioxide with the gaseous carbon dioxide. Hopefully you said the CO2 gas has greater positional entropy. The gas particles can travel all around their container and occupy many different positions, which gives them much more disorder than the solid carbon dioxide, otherwise known as dry ice. In the second one, hopefully again you picked the second answer, the nitrogen at 0.01 atmospheres, since we said it was a flexible container, is going to have a much greater volume. Remember, pressure and volume are inversely proportional. P1V1 equals P2V2. So the nitrogen at a much lower pressure will have lots of different spaces that it can occupy. It's not nearly as tightly packed as the 1 atmosphere nitrogen, which means it has much more entropy. Let's look at a couple more examples here. Again, I want you to pause the video and think so that you can decide whether these changes will be an increase or a decrease in entropy. The first one is solid sugar dissolving in water. It doesn't say that here, but it means in water. And the second one is iodine vapor, so iodine gas, condensing as a solid. Take a minute and think about these, and then continue with the video. Okay, hopefully you've given yourself enough time to think. Let's go over the answers here. In the first one, as solid sugar dissolves into water, its entropy is going to increase. That sugar, becoming aqueous, now can move freely throughout the water. It has many more positions it can occupy, so its entropy will increase. As the iodine gas becomes a solid, it will not be able to occupy as many spots, so its entropy will decrease. We'll have a negative change in entropy on this one. Again, we look at this same equation. Our second law of thermodynamics says the change in entropy of the universe is increasing, which is the change in entropy of the system and the change in entropy of the surroundings together. If delta S is a positive number, that means our reaction is going to be spontaneous. It will happen on its own. If delta S is a negative number, that means our reaction is not spontaneous. It will not happen on its own. And if delta S is 0, that means our reaction is already at equilibrium. Entropy can be dependent upon temperature as well. As we increase the temperature of something, we increase its kinetic energy, so the motion of its particles. We can see here that if we add some food coloring to hot water as opposed to cold water, the particles in the hot water are moving more quickly, so the food coloring is able to disperse more quickly. Having more kinetic energy allows for an increase in entropy as well. Let's think about the vaporization of water. Again, the delta S of the universe is equal to the delta S of the system plus the surrounding. If the water is vaporizing, is the delta S of the system increasing or decreasing? Again, you can pause the video and think about your answer for a moment. While you do that, consider what's happening to the volume of that water as a liquid as opposed to as a gas. Pause the video and think about it. Now, hopefully you've come to an answer. A mole of water, think about that as 18 grams of water, as a liquid does not occupy very much volume, whereas a mole of water vapor at STP is 22.4 liters. So the volume is going way up because the gas occupies much, much more space. There are many more places for each individual gas particle to go. This means delta S of the system is going to be a positive number. The delta S is increasing when we vaporize the water. This also ties back into earlier when we talked about how gases have much, much more entropy than liquids. So as our water goes from a liquid to a gas, its entropy increases. Also think here, if we're heating some water, we have to put energy into that water. So the surroundings are losing energy as the system gains energy. Vaporization is an endothermic process. You have to add heat energy to the water in order to vaporize it. Now, when we try and figure out whether or not water vaporizing is spontaneous, we know the water is gaining entropy, but the surrounding is losing entropy. So how do we know the sign of their sum? I've got a positive plus a negative. That means that our overall spontaneity is going to depend on temperature. My delta S of the surroundings is equal to negative the change in heat energy, delta H, divided by the temperature. The negative is just because of the direction that we're thinking about it going. And that's going to then affect delta S and give it the sign that we want it to have depending on the situation. So delta S of the surrounding is dependent upon the temperature. So now if instead of delta S of the surrounding, I substitute in my negative delta H over T, I can say delta S of the universe equals delta S of the system minus delta H over T, and then multiply everything by T to get this set up. So negative T delta S of the universe equals negative T delta S of the system plus delta H. Now the next thing we're going to talk about in the next video, because I'm running out of time, is this negative T delta S of the universe part, which we actually call delta G, or Gibbs free energy, as we see up here. But the thing I want you to think about in this scenario is, does water boil on its own? Well, that depends on the temperature, right? If I heat the water to 100 Celsius, it will boil on its own. But if the water is at 20 Celsius, it's not going to boil on its own. So the spontaneity of the reaction is dependent upon temperature. Now that's as far as I want to go with this video specifically, which is good because I'm running right up against my 15-minute time limit. Hopefully this worked out well. I'm going to do several more for our different sections of this unit. And then you guys can go through and watch at your own leisure.